So, in the previous session we have discussed about the most universal control configuration, that is called the feedback control configuration or feedback control strategy, right. But the feedback control strategy has got a problem. Here, once the disturbance affects the system and the output is changed already, then we are then the system is actually recognizing that there is a need to change the manipulated variable and the control loop gets activated. Controller starts controller starts generating the proposition regarding the change of manipulated variable, which is implemented via this final control element, and after certain time interval, just whatever I have discussed in the previous session, the state variable of the control objective again settles down to its set point. But over the time interval, we are getting the product stream, that is the typical distillate composition, the distillate, which should be a 95% pentane, but that deviates over the time interval from 95%. It may be 93%. So, you have to recycle it back to the feed tank or you have to discard it. So, this is a wastage of investment, right. So, this is typically we have to rectify upon changing the configuration. What we can do? Definitely in the new configuration there may be problems like it may not be as robust as a feedback control strategy. So, the thing is here, in order to improve that specific speed of this control action, we go for introducing the new strategy called the feed forward control strategy, right. So, it is the feed forward control strategy. So, here again we have, let me draw the distillation column once again. So, we have the feed flow rate F, ZF, TF, there is a total condenser Q dot C and reflux valve which adjusts the reflux ratio, right. This XD, D and here it is R being adjusted. We have the partial reboiler, the heat input rate in the reboiler is Q dot R, is generating the vapor and we withdraw the bottom product. Now, you see, in order to implement this feed forward control strategy, we have to identify the disturbance, the most potent disturbance which often deviates from its design value and cause the control objective to deviate from its set point. So, let us say for example, we have identified, so this F has been the flow rate of the feed has been identified as the most frequently changing input, thus a potent disturbance, most frequently changing input, thus a potent disturbance from its corresponding design value. So, we have identified upon checking this data on the device and therefrom we have identified it. Now, we will implement the feed forward. So, what we have to do? We have to continuously measure the flow, right. but we will write it as CIT. Why CIT? Because finally our objective is to control the composition, not the flow, right? So it's a part of the control loop which is controlling composition. So though we are measuring here the flow, but we will call it a CIT. So from there it goes to composition controller, which will be supplied with the set point, this configuration, right? We will discuss about the feed forward this configuration towards the end of this specific classes or these lectures. So here this controller, composition controller, is receiving the current value of the most potent disturbance. It will check the error, and accordingly, if this is the change of the flow rate, what will be the corresponding change it's going to happen in XD, that it is inbuilt, that program or the code or the model is inbuilt in the controller. Based on that, it may be some empirical model as well, right? So based on that, it will generate some proposition regarding the change of this reflux ratio, which will be implemented via this final control element, which is the reflux valve or the pneumatic control valve fitted in the reflux line. So if I try to implement it or generalize it with a block diagram or schematic, then this is the system, these are the solid lines, measured disturbance, this is unmeasured disturbance, and here we have the measured output, which are my control objective, and there will be some unmeasured output as well. Manipulated variable. Now note that this here we are drawing the general system, right? It has nothing to do in general in this form of diagram, it has nothing to do with the feed forward control strategy. Now we are going to implement this feed forward control strategy here. But point to be noted is that when I am implementing the feed forward control strategy, actually we do not measure the control objective. Here I am not measuring XD, right? So don't get confused that why I am writing here the measured output and the control objective, something like that. Okay, it's independent of this loop strategy, the feed forward control strategy. So measured disturbance, we will have the measuring device, then there will be controller, controller will be supplied with the set point values, and from the controller we will implement the controller's decision on the manipulated variable line, right? And at each and every interface there will be a final control element. So this is the feed forward control strategy. Okay. Now this has got a high speed of action. However, it is non-robust. Why it is non-robust? Because let us say the temperature of the surrounding drops abruptly by 6-7 degree. So, there will be increased heat flow. As a consequence, the temperature in the trays will be changing, which will change the equilibrium relation and finally the distillate composition, right. But that remained unmeasured, okay. That remained unmeasured. Because we haven't considered the Ts as my potent source of disturbance. So, whatever we go on considering as my potent source of disturbance, if that only changes, we will have a high speed of action. But for all the other disturbances which I am not going to measure because of this, right, the system may deviate from its set point and that I am not going to measure it. So, feed forward is non-robust control strategy, however, it has got a high speed of action. So, it is recommended that we should not use, recommendation is use feed forward loop coupled with robust feedback loop, right. So, that is everywhere we have to do it. Now, next here let's think of a practical problem. Now, we have stated that it is pentane and hexane, right. So, how we are going to measure it? Okay. If I am going to measure this composition analyzer, what is that? It must be a GC, a gas chromatograph. What is the cost of the gas chromatograph? Around 20 lakhs, right. Medium reliability standard gas chromatograph, which can actually measure the mole fraction or mass fraction of pentane in a pentane hexane mixture or solution is around 20 lakhs. So, you are producing commercial grade pentane and for which your investment to implement a feedback control loop here I am not for feed forward. In feed forward I am not measuring the composition, but that is non-robust. As mentioned that we have to always use it in coupled form with the robust feedback loop. So, the thing is we are it's totally not economically feasible to use a GC for a production of commercial grade pentane. And that is a problem with all composition analyzer. So, the fact is that these composition analyzers, let me just write it, okay, here. Composition analyzers are mostly high cost devices, right. Low cost CITs are not reliable at all, right. So, that is a problem. So, how to mitigate that problem? We actually there have to think alternatively in terms of mathematical model. So, what is that? If I measure this temperature of individual tray and if I know that vapor liquid equilibrium relation, next I will go on solving the mesh equation which I have discussed about in mass transfer. Let us say we will be solving this mesh equation and we will try to predict that what will be this Y1, right. Upon measuring the temperature profiles in that column. We will measure the individual temperatures of that column or the individual tray temperature of that column, we will get a set, right. So, from there we will use the equilibrium relation, we will use this material balance, we will use the summability, we will use the enthalpy balance, and from there finally our output will be this vapor composition from the first tray. Okay. So, if I can predict y1 or if I can think of such function, this function is just for representation, it may not be directly a function, it is after doing some solutions and solving this mesh equation simultaneously we will get this. Let us say it is T1, T2, these are the variables which we are going to measure, and finally our objective will be to predict y1, and which is same as that of the distillate composition because we are using total reflux, right. So, the point is here if you look into that general structure of that system, do not consider this control loop what we have drawn for feed forward strategy. So, there the problem is our measured output is not my control objective, whereas my unmeasured output is my control objective, because XD I am not measuring, that is my control objective. What I am measuring? The temperature gradient in that tray, but that is not my control objective, right. So, that strategy is very, very evident, and actually it is implemented in composition control in all chemical process plant nearly, right. So, this gives rise to something called inferential control strategy. So, our next topic of discussion will be the inferential control strategy. Here unmeasured output is the control objective. That is the problem. So, let me draw again the distillation column. The feed F, Z, ZF or whatever Z, TF, condenser, distillate, R, partial reboiler, this is Q dot R, this is Q dot C. Right. Now, what I am going to measure? I am going to measure the temperature. So, this is TT1, and finally, in this way TTN, right. Now, we will feed it to this block which is referred in schematic as estimator, right. What is the inbuilt functionality? That y1, this is y1 which is same as xd, is a function of T1, T2, Tn, right. This will give you the estimate of xd that we feed to the composition controller, which is supplied with xd set, the controller will propose the corrective action which will be implemented via this reflux valve. Right. So, from here we are measuring something which is not my control objective. Then through this estimator we are predicting what is the expected or what is the current value of this unmeasured control objective, and rest is same as the feedback control strategy, right, or the feedback control loop here. So, schematic of inferential control system is this. We have the system, the same diagram once again. So, this is a general diagram. Here particularly from the perspective of inferential control strategy, all the disturbances are unmeasured, but we write that as measured disturbance, unmeasured disturbance, manipulated variable, measured output, then unmeasured output, and these unmeasured outputs are my control objective. Right? So, that is the system in case of inferential, or where we can implement this inferential control strategy. So, first we will be using the measuring device to measure this output. So, this is the measuring device. Next, we feed it to the estimator. Estimator will generate the measurement or estimate of this unmeasured output, that is my control objective, which will feed to the controller, and definitely the controller must be supplied with the respective set points, and controller's decisions will be implemented on the manipulated variable line through the interface of final control element. So, that is the schematic of inferential control system. Right. Now, in all this, starting from feedback to feed forward to inferential, what we need actually, the controller, you see, it is receiving the, say this is the controller, it is receiving the measured output in general, or measured or estimated output, right, and it delivers the required value of manipulated variable to reduce the error to 0, right. So, how the controller is doing that, or how the estimator is estimating this unmeasured output, that is the control objective, from measured output which are not the control objective. So, inherently that needs the input output model of that system, right. So, in general it needs the I/O model of the system. So, we have to, what I am trying to point out, that to implement or design a controller, right, primarily or to understand the dynamics of the system if a manipulated variable is changed or if a disturbance is changed, how the system is going to respond. So, that needs input output model of the system. That what is that? Input output model is y1, or rather we can write y bar is a function of manipulated variable and disturbance, where y bar is y1, y2, yn, right. M bar is m1, m2, this m, or rather let us say m capital M, and d bar is d1, d2, finally dp, right. So, output is expressed as a function of input variables. The input variables consist of manipulated variable and disturbance. So, this is the general functional form of input output model. Now, how to derive this input output model? We have to actually formulate the state model of that system, right. In the form of certain differential equation, we have to formulate the state model. There it will be explicitly not this sort of functionality, not the algebraic functionality, but rather including the derivative and integral operators, and will be called the state model, right. So, I will give you the example. So, first we have to develop the state model of the system. So, state model, and from there we have to generate, upon solving it, the input output model. And state model may be an ODE or PDE, right. So, when it will be an ODE and when it will be a PDE, that we have to understand. Let a state variable be eta. If eta is a function of space coordinates and time, if it is a function of space coordinate and time, then we call it a distributed parameter model. Right? And eventually this is a PDE because there are multiple independent variables. So, distributed parameter approach, or rather we will go for, let us write okay, distributed parameter model. So, the respective state model assumes the form of PDE. Now, you solve the PDE, you get input output model of the system. Right? On the other hand, if we can safely consider eta to be a function of time only, right? The typical example we have seen in heat transfer in conduction, that when the Biot number is much less than 0.1, we can go for lumped parameter model, right? Where the temperature inside the solid doesn't change with the space coordinate, it's uniform throughout. So, this is called in general the lumped parameter model. Right? So, lumped parameter model definitely gives you ODE as the state model, because there is only time which is involved here. And solve that ODE, we get the input output model of the lumped parameter system, right. So, these two are the two different approaches. So, how will you write or how will you develop these state models? So, how to develop the state model of a system? So, obviously the answer is combine the appropriate conservation equation with the rate laws, with the applicable or the pertinent rate laws. Now, see the conservation equation, these are the outcome of thermodynamics, right. Thermodynamics only can preach about the possibility of a process or what are the variables to be conserved in a system, whereas rate laws are outcomes of kinetic study, right. And most of the rate laws are either, or most of the rate laws, or the rather we should say the rate laws are either phenomenological or empirical. Like the Fick's law of diffusion, it's a rate law. So, it simply represents the rate of transport by molecular diffusion, right. So, it's phenomenological equation. So, rate of momentum transport is given by the Newton's law, which is also phenomenological. Whereas, empirical rate laws, the typical example is the heat flux convective is H into delta T. So, H is an empirical coefficient, mostly we find it through these experiments and empirical correlations like Ditas Volta, C delta T for pi flow and different others, right. So, this is an empirical law. Actually, there is nothing called H from the physical origin of that system. What we do? We simply combine this Kf with the delta, which is effective this film thickness, effective film thickness. So, Kf divided by delta, we call it, we lump it into H and we generate this rate law as the convective flux as H into delta T. So, this is an empirical rate law, okay. Whereas, conservation equations are not empirical, like conservation of mass, it is a universal physical rule, right. Conservation of momentum, which is via this Newton's law. Then conservation of energy, which is the first law of thermodynamics, okay. So, for any system, or rather here this system, let us say we have input streams I equal to 1, 2 up to n. Actually, we are using what? We are using this conservation equation for a typical given amount of mass. This we are coupling with the Reynolds transport theorem, and finally we get this sort of a conservation equation for a controlled volume rather, right. So, here it is J equal to 1, 2 up to m. Now, conservation of mass, how we can write that? It is simple, ddt of rho into V is equal to sum rho I Fi sum rho j Fj, where j stands summation over m and I summations over n, where rho and V bar are the density of that specific material inside this control volume. So, here the system actually refers to the control volume, right. So, conservation of component mass. That's simply an extension of the total mass. So, d dt of Ca into V is equal to Fi Cai, F is the volume flow rate, minus Fj Caj, J equal to 1 to M, plus minus R. R is the reaction rate, it may be a generation, R into V. So, R is the specific reaction rate. It may be a generation rate, it may be a consumption rate. So, based on that we have to choose the plus or minus. And conservation of energy. Right. So, ddt of this E, okay, this I think we can reframe it, just a minute. ddt of E, yeah, which is ddt of U plus Ek plus Ep is equal to the sum Hi rho I Fi minus Hj rho j Fj, right. H is the specific enthalpy, that is the enthalpy per unit mass. Rho and F gives you the mass flow rate. So, that is the total inflow of enthalpy minus outflow of enthalpy plus Q dot minus W dot. Yes. Okay. And Q dot we consider to be positive if heat is given to the system, and shaft work is positive if it is being performed by the system. So, that is why it is Q dot minus W dot. So, that is the conservation of energy. Majorly we are going to use these three conservation equations in different systems to generate the model, right. So, first let us discuss about the lumped parameter model, different examples of lumped parameter model in chemical process industry, which we can approximate as lumped parameter. So, examples of lumped parameter models. First, it's a very simple liquid storage tank. Right. The same system with which we have initiated our discussion, F, H and Fi. Right. So, definitely we are going to apply the conservation of mass, that is the total mass. And we will go on listing the assumptions as we try to simplify the system. So, here it will be ddt of A into rho into H, where A is the cross sectional area of the tank. Right. So, that is equal to rho I into Fi minus rho into F. So, the same rho with the same liquid is flowing out. So, you can write rho into F, you do not need to write rho j Fj. So, now you go for assumptions. Liquid is highly incompressible state of matter and there is no heating. So you can assume incompressible system. Right. So obviously it is left with ddt of A into H is equal to Fi minus F with assumption 1. So next it is A into dH dt, because A is constant, Fi minus F. So that much we can get from conservation equation only. Now F, see, F is a function, actually a function of level, right? We have adjusted the valve and F is a function of level. So here we have to use the rate law, which is F is a function of H, right? So we can think of that, okay, how to get the rate law. Let's apply Bernoulli between point 1 and point 2. Bernoulli's equation between point 1 and 2. What I get here, it's atmospheric pressure, so it's 0. P1 by rho, it's 0. Alpha 1 V1 bar square by 2, 0, plus G into H is equal to P2 here, it's releasing into atmosphere once again, maybe, right. So it is 0. Here we can write then alpha 2 into V2 bar square by 2 plus head loss. Now head loss for this pipe segment, let's think this pipe is of length L and its diameter is D, right. So it is Fd, Darcy's friction factor, into this L by D into V2 bar square by 2. Plus minor loss, there will be some contraction. So it is 0.4 into V2 bar square by 2. And loss for this valve, right. So we can write again Fd into Le by D, the equivalent length concept, into V2 bar square by 2. So that's the thing, right. So we get V2 bar square by 2 multiplied, or rather we can write it as this, a constant K into V2 bar square. So V2 bar is equal to G by K into H under root. Okay. So F is equal to V2 bar into pi by 4 D square. So you can write it as a constant beta into root H. So that becomes my rate law. So if you ask that where is the source of empiricity here? Definitely it is empirical, because this friction factor itself is empirical. You have got the idea of friction factor from dimensional analysis, and you are getting the exact value of the friction factor from either the Moody's chart or by using the Colebrook relation or Blasius relations, which are also empirical. So this is a rate law and that's empirical. So my equation becomes A dH dt is equal to Fi minus beta root H, right. So beta is dependent on, precisely it is dependent on the opening or closing of that gate valve. So if I am given with the system or the state equation just as I have marked it, right. Now let's identify what are the input and output. So First let's write output, which is state variable also, and here this is also my control objective. That's only H. Now input, manipulated variable and disturbance. Now disturbance is Fi and manipulated variable is beta, right? We cannot write it as F because there is no F present here. Already we have used the rate law. Okay. So as you go on adjusting the valve, the hand wheel, maybe it's a manual control. So as you go on adjusting the valve, you are basically adjusting beta and you are getting the controllability of that system, right? So, but here if you look into this system without using the rate law, F will be your manipulated variable and Fi will be the disturbance, H as usual will be the state variable. So, thing is that this is my input, not the input output model. Input output model is problematic here to solve this equation. Why? Because it is nonlinear ODE. Nonlinear ODEs cannot be analytically solved. So we have a specific topic which may be discussed, we will be discussing maybe after one or two sessions, that linearization. And that's why we have to linearize. See, we have to linearize this beta into under root of H by using Taylor series expansion, and then it will be converting into a linear equation, but the accuracy of the mathematical model definitely will be compromised, right? Because you are replacing the true term by an approximate term, and as a consequence your simulation or the simulated prediction of H for a given change in Fi, right, or given functionality of Fi is definitely going to deviate from the true value of H. But we will introduce strategies by which we can minimize the deviation. Okay? But this is, for the time being, it's a mathematical state, or this state model, a lumped parameter model, where we have identified the manipulated variable to be beta and disturbance to be Fi. Correct? So, that's about the liquid storage tank. So, next let us go for another one, which is definitely we have to use maybe more than one conservation equations and rate laws. So, it is stirred tank heater. This is also a lumped parameter model. So, example 2 is stirred tank heater, right. So, what is that? So, it is a steam coil where we have steam and it is only exchanging latent heat, condensate, and there is a starter. We have Fi, inflow temperature Ti, F, T, and the heat flow rate is Q dot, right. Why it is a lumped parameter model? See, truly, if I am feeding a starter, very high powerful starter, still there will be temperature variation, different temperature zones here, right, close to the heater it will be a high temperature. But if I go for a theoretical limiting approximation that the starter is so efficient, it homogenizes the thermal state of the liquid, then we can say that T perfect, or this under the assumption of perfect stirring condition, T is only a function of time, not of space. And whenever I say it is a stirred tank heater, actually it is not an assumption, it is given in the problem statement that you develop a mathematical state model of the stirred tank heater. So, already stirred tank means it is a lumped parameter, T is a function of time only. So, we do not have to list it as assumption. So, assumption number 1. We'll go on developing, but let's focus on the conservation equation. So directly we can write that ddt of A into rho into H is equal to rho I Fi minus, as it is start, all properties of outflow and the property of the tank remain same. So F into rho, right. So first we can also assume here incompressible liquid, though it is to some extent questionable. However, this is true if Ti and T, they are close to each other, maybe a difference of 10 degree or 15 degree, right, or even 40 degree. From 20 degree you are going to 60 degree. So let's say it's a water heating system, and we can safely disregard for this primary or preliminary model, we can disregard the variation in density and we can assume incompressible liquid. So essentially we go for A dH dt equal to Fi minus F, right. So that's my equation 1. Next we have to apply, definitely the next one is the conservation of energy. So ddt of U plus Ek plus Ep, we are writing it as du dt. Why? Because the inflow kinetic energy and potential energy, definitely they are different, right. Because if we consider this as datum, there is a potential energy, and here it is the potential energy 0 state, and kinetic energy too will change, right. But that is insignificant compared to the change of internal energy. So we can write that d of Ek is d of Ep between inflow and outflow is 0. So we can safely approximate it as du dt. So du dt equal to Fi rho I Hi minus F H, or let's write, as we have used H, so let's write H prime, where H prime is the specific enthalpy of the outflow, right, plus Q dot, Q dot is the heat inflow rate. Now you see that H or dH is equal to du for liquids. So third assumption, dH is close to du, right, because Cp, Cv are same. And fourth assumption is ideal liquid or ideal fluid, that is dH is equal to m Cp dt, that we can use, right. So here d dt or dH dt, because u dH and du are same, it's equal to d dt of rho A Cp rho A H, H is the level, that is the mass, into Cp into T, right, and that's equal to rho I Fi Cpi Ti minus rho F Cpt plus Q dot. So essentially you see that Cp, Cpi, here Cp, so there is practically insignificant variation. So we write constant specific heat. Okay. So we have now rho is constant because of incompressible flow, Cp is constant, area is constant. So rho A Cp ddt of H into T is equal to rho Fi Cp Ti minus rho F Cpt plus q dot. So, essentially it will be ddt of h into t is equal to this Fi into Ti minus F into T plus q dot divided by rho Cp. So, next we will split this derivative into two. So, h into dt dt plus t into dh dt is equal to Fi Ti minus Ft plus q dot divided by rho Cp. So, h dt dt as remaining same. So, t dh dt, or sorry, there will be an area. I think that area, sorry, here area was there. So, area will not cancel out. So, h. So, this is a, right. So, a dh dt is Fi minus F. So, here I will have Fi minus F is equal to Fi Ti minus Ft plus q dot by rho Cp. Now, this Ft minus and Ft minus, they will cancel out, and we have AH dt dt is equal to Fi Ti minus T plus q dot by rho Cp. So, this will be my equation 2. So, this is equation 2 and this is equation 1. Finally, we have got this without so far using the rate laws. So, with this structure, next see what are the state variables h comma t. Here we were not interested about the control, we are specifically focusing on the this dynamics of that system. State equations 1, 2. Input, definitely we will have manipulated variable. What are the manipulated variable? We have here in the first equation, that's F, in the second equation, that is q dot, and the disturbance, definitely in the first equation it is Fi, second equation both are present, there will be additionally Ti. So, that is my summary, right, so far without using rate laws. Now, we use rate laws. So, see, if we have got truly it is beta into root h, but in many cases, as I have mentioned, that this can be linearized, and by the analogy of Ohm's law or linear rate law, we can go for linear rate law upon linearization of root h, which is a nonlinear term. What is that? F is equal to delta h by r, and here delta h means what? The difference of height. What is the height difference? H, and here 0. So, it is F is equal to h by r, where r is basically the hydraulic resistance of the system. Resistance of the pipe and the valve, right. So, let us use this linear rate laws, which is an approximation, but still we can work with that. So, if I use the linear rate laws, say A dh dt will be equal to Fi minus h by r. Let us call it equation 3, right. And here this q dot, we can replace it by u into At into T steam minus T, where u is the overall heat transfer coefficient, At is the area of the coil, Tst is the steam temperature, right, steam at temperature Tst. Okay. So, we can modify this equation as Ah dt dt is equal to fi ti minus t plus u at tst minus t divided by rho Cp. Let us say this is equation 4. Now, for that we can actually introduce another this